So we finished, oh, maybe not here. Let's go back again. We have, review again, the classes of amino acids. They're nonpolar, polar, acidic, and basic. Remember we said if we only see carbons, hydrogens, or a buried sulfur or buried nitrogen, or a nitrogen that won't accept a proton, then those are going to be your nonpolar ones. So again, if you just see carbons and hydrogens, you're going to say nonpolar. And we went through the description of each of those. Cysteine, remember, here they're classifying it as nonpolar, but I classify it as polar. Polar, you're going to see the OH, the hydroxyl group, or an amide group. Remember, an amide group is the amine group next to a carbonyl. So that you're going to see either an OH or an amide group for the polar. Acidic, you're going to see an acid. And basic, you're going to see a nitrogen that is able to accept a proton. So you can see what we've done is we've shown this acid group above its pKa where it's already donated the proton. And we've seen here the base below the pKa where it has the proton. It doesn't have to have it, depending on the pH. So the question is, does the base have to have a proton on it? At neutral pH, the bases here have the proton. It's protonated. However, a base is a proton acceptor. Now, remember, an acid and a base have a pKa. So at pHs below the pKa, they have the proton on it. At the pKa, half of it is protonated, half of it has donated the proton. So half is in the acid form with the proton, half is in the base form, giving up the proton. And then above the pKa, it's given up the proton. Acids donate protons very easily, so they have a very low pKa. So here we can see that at neutral pH, it's going to be, and we're going to cover this later, that it's already given up the proton, so it's in its ionized form. Here, neutral pH, we're below the pKa of the bases. So in general, when you're identifying these acids and bases, you're going to see an acid group, whether with the proton or without the proton, in the acid, and you're going to see a nitrogen-containing group that is not buried and is not with a carbonyl. Alex?
So if you see the base with the above the pKa, it wouldn't have its proton on there and everything?
That's right. If you see a base and then the pH is above the pKa for that base, generally the pKa's for these are 9 or 10, then it would not have the proton on it. And that's what we're going to spend time on today. So we're going to fully understand what I just said, all of us. Now, I do not require that you remember these, but I just want to point out that there are a lot of derivatives of amino acids. In groups or in areas where we need a lot of hydration, you'll see hydroxyproline. We add groups to these other things. So hydroxylysine and hydroxyproline we'll see in connective tissues such as collagen, and what that hydroxy group is, it draws water to it. Thyroxine is only found in the thyroid gland. Remember, you need the iodine from the salt, so we use the iodized salt so that we can produce our thyroxine for our thyroid gland. Neurotransmitters can be derivatives of glycine. A glutamine derivative is serotonin, and a tryptophan derivative is serotonin. And melatonin is also a tryptophan derivative. My husband and I take this at night to help us sleep. But if you take too much, it's like you have a hangover the next day. You want to just sleep all day. So be very careful if you take that. Does anybody take melatonin? You have before? Does it help you guys?
No.
Sleep?
I've never experienced anything different.
Yeah. It makes me sleep hard. Yeah, it makes me a zombie. You know what helps me better is Benadryl. If you can't fall asleep. Yeah, when you get to be elderly like me, Sleep comes easy, but not, it can't stay asleep. So you just take a little bit of children's Benadryl and you're out. So again, thyroxine, and indole acetic acid, they are found in the thyroid gland. All right, so let's talk about what happens to our amino acid as we change the pH. And I know this is going to be a little dry. I'm going to try to make it as entertaining as possible. However, the reason why we're learning this is it's critical to our folding of our proteins. So you have the peptide chain, the protein chain. Peptides are short proteins, right? 50, that's right, 50 amino acids for us. And then the proteins and peptides will fold to make the native structure, the active structure. But the way it folds is dependent upon whether things are charged or uncharged. So what we're going to do is take a look at the amine group and the carboxylic acid group, and possibly any side chains, the acid and base side chains that can accept a proton or donate a proton. So what is going to change as we change pH? What is pH a measure of? That's right, hydrogen ion concentration. So as we increase pH, what are we doing to the hydrogen ion concentration? As we're increasing pH, we're decreasing hydrogen ion concentration. So the way I want you to think about all of this as we go through the next few slides is when you're in an environment that's low pH, your environment has a lot of protons around. So what it's going to do is it's going to stuff protons on your structure wherever there can be a proton. And as you raise the pH, you're going to ionize, pick off those protons. You're going to get low-hanging fruit first. You're going to ionize those protons that are easiest to ionize first, and then those that are harder to ionize. So think low pH, high proton, high hydrogen ion concentration. Everything that can have a proton will have a proton. As you raise the pH, you start ionizing or you start neutralizing those protons. Where do we see an ionizable proton? Well, here we're showing neutral pH, but in an alpha amino acid, we see an ionizable proton on the amine group. We see it on the acid group. Here we've already shown it that it's already been ionized. It's already been neutralized. And we can see it on some of our side chains. Here we're showing the pKa for the acid group, the base group, or the amine group, and our side chains. So notice that our polar, nonpolar side chains do not have a pKa for their side chains. There are some polar ones, histidine and cysteine, that can be ionized. But for the most part, we're going to leave it to the basic and acidic side chains. Aspartic acid and glutamic acid, but histidine and cysteine can also have a proton be ionized. But we're not going to focus on those. So right now, what we're going to do is focus on our acid group and our amine group. Notice that the acid group has a pKa of about 2. And remember what the pKa means. If your pH is at the pKa, half of the molecules have the hydrogen on in the acid form, and half of the molecules have the proton donated, or in the base group, base form. So at this pH, so for glycine, at pH 2.34, we have half of it that has been is intact with the hydrogen on the group, and half of it with the hydrogen off of the group. Now the amine group. The amine group has a pKa between high 8s and 10. So at these pHs, below that, we have the proton on. At these pHs, half the group has the proton on, half of it has the proton off. Above it, we have proton off. It's been ionized. And that's the pK for the acid group?
Is that the same thing below the protons on and above?
Yeah, yeah. So that's my Karate Kid. Did anybody watch it this weekend? Karate Kid, proton off, proton on, wax off. So I talk about that a lot as we go through. I bet with all the football, we're not able to watch the Karate Kid. But all right, let's take a look at this. Here we just show a ball and stick, but I think it's easier to take a look at the bottom part. So follow me here. Here's the acid group. Here's the amine group. Here's the alpha carbon with its hydrogen and the R group. So right now we're going to stick with saying that this R group is a non-ionizable side group, that it doesn't do anything as the pH changes. And what we're doing is we're going to be at low pH here. So let's say we're at pH 1. Let's say up here we're at pH 12. And let's say here we're at pH 7. So as we go up, we're going up in pH. So when we're at pH 1, everything that can have a proton on it will have the proton on it. So here's our acid. This is the proton on. Here's the amine, NH3. Remember pH 1, high hydrogen ion concentration means that there's hydrogen ions everywhere. It's going to push it in to the structure. Now, acids readily donate their protons. Strong acids completely donate it. Weak acids, not so readily. So we have to get up to pH 2.34 to say that half of these protons have been donated. So at that pH equal to the pKa, we have half of this form and half of this form. So below this pH, 2.34, we predominantly have that one. Above the pH 2.34, we predominantly have where the proton is off. So again, let's remember, the pKa, equal amounts proton on, proton off. Below the pKa, more proton on, it's more acidic. Above the pKa, more proton off. The first pKa we get to is for the acid. Yes, COOH is the acid, and this pKa corresponds to the, corresponds to the acid. This pKa corresponds to, corresponds to the amine group. So you can look back in the last slide, and it has that table of the pKa's, which I will supply to you on the test. So here, again, predominantly below the pH, we have protons all over the place. When we start to raise the pH, we're going to take it off the acid first because it's easier to ionize that one. It's harder to get it off the amine group. So at pH 7, we're in between the two pKa's. We predominantly have the proton off of the acid group, And because we're below this other pK, 9.69, the proton's going to be on our NH3. So that 3 means you have the proton on. The 2 means the proton's off. So once we're above the pKa for the acid, the proton's going to be off completely. You're never going to get it back. Now, until we reach the pKa for the amine group, that proton is predominantly going to be on. Once we reach the pKa, it's going to be half off, half on. Once we're above it, proton's going to be off. So now you can say what the predominant form is at different pHs, given the pKa's. So that's what I'm going to do to you on the test. I'm going to give you pKa's. I'm going to give you an amino acid. And actually, I'm only going to give you what the side chain is of an amino acid. I'll give you what the side chain is of amino acid. And I'll ask you to draw the predominant forms at the different pHs. Yes?
So does the acid part always donate first?
Yes, the acid part always donates first. It always has, and you can look at the table in the last slide. It always has a lower pKa. It donates first because it's easier to get the proton off. An acid donates a proton. A base accepts one. So they're only doing their job. You can't criticize them, right? So the acid is donating it readily, easier. The base is keeping it more. Yes, Alex?
When we say half and half, like the pKa of 2.34,
Yes.
Does it mean like about like half of the like 0.5? If you have 1 mole, like 0.5 moles, or like have 1 part going on and then have it like off?
That's right.
Okay.
So the question was, at this pH of 2.34, if we had 100 molecules, 50 would have the proton off, only for the acid. This pK only has to do with the acid. Okay, so this pK, we're saying that the proton is off for the acid, because this is only talking about the acid. And then 50 would have the proton on. Notice that it's a double arrow, so there's equilibrium, but we're not going to get into that. But I'm going to ask you, draw the predominant form at these different pHs. What does that mean? You're going to have to know what the backbone looks like, right? You're going to have to know how to draw the structure. You're going to have to know how to draw this.
Just that one?
Well, I'm going to give you what the R group is, so you can draw that in. So you're going to have to know how to draw all of these. You're going to have to basically do exactly what is here. But I'm going to ask you different pHs.
So you're just going to have a different R group?
You don't have an R group here. You just have R. I'll tell you what the R group is. Might be glycine, might be something that's not alanine, something that's not ionizable. I'll tell you what it is. Alanine is this structure. Draw the alanine at, or has an R group of this structure. Draw the amino acid at pH 1, 5, and 7. I might do that.
But is this a backbone for all of them?
Yeah, this is the backbone. This is an alpha amino acid backbone.
And you'll give us the pKa's?
I have to, yes. I have to give you the pKa's and what pHs I want you to draw it at.
Okay.
Yes.
So we'll do the same thing for R as we do for the acid and the vector?
So is your question if I give you an ionizable R? I'm not going to do that to you on this first test. Okay? I am not going to give you an ionizable. We'll talk about it in class. Maybe we'll do a little bit with homework, but we're not going to do it on the test. Okay? I'm going to give you, it's just going to be the backbone for now. Yes?
So when you
have the proton off for like a pH of 1, like for the example you said, when you go to a pH of 5 and you haven't, is that still the for the acid?
Yeah. So the question was pH 1, the proton's going to be on everything. That's apparent. It's below the pKa. So here I'm showing pH 7.
So you don't have to go past neutral for it to affect.
That's right. The neutral pH has nothing to do with it. It could be pH 5. Just because we're above the pKa means I could do pH 3, and the predominant form would be this one with the proton off, because the pKa is 2.34.
So as soon as it goes over the pKa, that's when you lose the proton.
We're starting to lose the proton very early, but it's the predominant form. It means more. So it might, if we get to pH 2.4, there might be, if we have 100, there might be 51 that has the proton off, and 49 that has the proton on. But if I ask you what the predominant form is at 2.4, you're going to tell me the proton off form for that one. Okay. All right?
Sorry, I'm just getting confused if you change the numbers. So just say that's pK of 5.
No. The pK is always going to be about 2, and the pK is always going to be about 9. The question was, what if I ask you to draw the structure at pH 5? And it would still be this structure because we're above the pKa. So this is going to be anything, this structure is anything above 2.34 and below 9.69. Don't be scared about drawing the structure. You just have to know amine, alpha carbon, acid. And off the alpha carbon, you have the R group and the hydrogen. Yeah, I think this class is a little deceptive because it's a lot of independent study. There's not a lot of physical work that you have to do for it. There's no mastering chemistry. And so you have to practice drawing these things on your own over and over. What people have done who have been very successful at the exams have printed out multiple copies of the homework and have done them over and over again. All right? They just go through and print them out and just do it until you don't need to look at your notes. So I think that's a good thing to do. All right, we're going to go over it a little bit more because that's what I do. That's how I roll. All right, so this is just a different view of what we had here, okay? Imagine this as a titration curve. So here you can see the pH is going up. Well, the pH would be going up if we added sodium hydroxide, correct? So we're going to have a similar thing here. The pH is going up. We're adding sodium hydroxide. So let's take, and this is the same thing, we're starting with this, and we're going to increase the pH. You can increase the pH by adding hydroxide. So which proton is going to be ionized or neutralized first? It's going to be the acid one. So first is going to be the acid one. Once that's completely neutralized, then it's going to be the amine one. So remember that the acid one is going to be neutralized first because it's a proton donor, and then the amine one because it's a proton acceptor. So it's much more difficult. Do you guys remember Le Chatelier's principle, where if you apply a pressure on one side of a reaction, it's going to shift to relieve that pressure? I like to think of it the same way. The acid proton, so imagine this hand is the acid and this hand is the base, and they're holding baseballs, and the baseballs are the protons. And at first, there's baseballs all around, and say the room is filled with kids, okay? And there's baseballs all around. So the kids aren't trying to rip the baseballs out of my hand. As we raise the pH, the baseballs are going out of the room. So the kids now want the baseballs out of my hand. This one, because it's an acid, it's a proton donor, it's going to give up that baseball easier to the kids in the room, right? So first, it's going to give that up once the room starts emptying of baseballs. Then the base one, though, it's a proton acceptor. Its job is to hold on to that baseball, proton acceptor. This one, acid, is a proton donor, so it's going to give up that baseball pretty easily. So here, it's going to hold on to it until you only have the bully left in the room, right? And he's gonna rip that proton off of my hand at a much higher pH, because at high pH, there's no protons left in the solution. So it's going to keep it. I don't know. The weirder it is, the better you guys remember. I don't know. Remember, the job of a base is to keep the proton. So that amine is going to keep that proton on it until pH 9, 10, until there's hardly any protons in that solution. It's not going to neutralize it, because what this hydroxide is going to do is it's going to neutralize the easiest proton first. And here, this is the easiest proton. Then later, it's going to neutralize this one. Okay, so let's look at it as a titration. We're adding sodium hydroxide in at no addition of hydroxide. We are at a very low pH, and you can see that we have the proton on the acid and we have the proton on the amine. So here it's proton on and proton on. On and on. We start dripping in hydroxide, going up and up and up, drip, 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 drip. What we're doing is, as we're dripping, each drip is neutralizing a little bit of this. So as we go up here, we're starting to neutralize these, and we have fewer and fewer proton ons for this one. At this first pKa, we have half. I'm sorry. We have half of these two. So the concentration of those two, proton on and proton off, are equal. Which one do we have more as we continue to drip hydroxide in? Do we have the acid form or the conjugate base form? The conjugate base form, until it's fully neutralized. Okay? Here, when it's fully neutralized, we don't have any more of the acid form. So this is your equivalence point. Once that's fully neutralized, which proton is the hydroxide going to go after? There's no more baseballs in my acid hand. It's going to go after the baseball in your base hand. So it takes more and more and more, and we start to go after that one. So here we're going to go after this one. Now here we have at the pKa, we have this pKa, we have equal concentrations of proton on and proton off until we keep going, and we have more of the conjugate base, more of the NH2 here, until we only have that. So at pH, say, 14, all of the protons have been ripped off of our amino acid. So what I like to do is say, okay, we predominantly have this guy here. We predominantly have that guy here. Of the two, we predominantly have the base here and the acid here. Any questions so far? Yes?
If you're not testing us with R, how will the question be different on the test?
The question's not, if I'm not testing you in R and I tell you what the structure of the R group is, it is not different than this. It's not different at all. You just have to know this. It's your responsibility to absorb it and know it and be able to repeat it. So make up your own questions and say, okay, this is what it is. Yeah. There's another new term here, this PI. It's called the isoelectric point. We're going to talk about it later, but the isoelectric point is the pH in which you have only a net neutral molecule. So here we have positive and negative on the same molecule, and we only have that. So that's where we call the isoelectric point. We're going to go over that for the definition later. Slide 27. All right. Here, even though we said histidine is a polar, you guys have a question?
Every time you have the pK 1 is 1.82, you're saying the pH is also 1.8?
At that, yes.
Just at that point.
Yeah, just at this point. Yeah. But that's where the PK is, the first PK. And so they're showing you along the titration. All right. So histidine, and I'm not going to focus on this. It doesn't act as an acid or a base, but it can accept and donate a proton. But because of the position in where the pKa is, it makes it a more of a polar one. So it's not a low or a high pK, it's a more neutral one. So that's why we talk about it. The pK2 is 6. So it doesn't make it an acid or a base one. I know it's a little complicated, so I'm not going to focus on this, and I'm not going to test you on an ionizable side chain. I just want to show you that there are situations where you have a third pK value. And what you have to look at is saying, okay, again, let's take a look at this one. Now we have 3 positions that you can have protons on. When you have the lowest pH that you have, then protons are on all of them. You have to know what the pKs are and what they correspond to. I'll tell you that. I'm not just going to give you pKs. I'll say the pKa for the acid is this value. The pKa for the amine group is this value. So I'm not just going to throw values at you. So, and you'd be able to look those up. So here, what we have is a pK1, and that has to do with the acid. So above it, we have and they show it, the proton is off there. The pK2 has to do with that proton. So at that pH, you have half on the side chain and half off the side chain. Again, still, we have the proton off of the acid group. So here we're showing where we're above this second pK for that side chain, so where that proton is off of there. The proton's still off of there. Once you take it off, it doesn't go back on when you're raising pH. But here, we're still below this pK, so that proton's going to be on it. So I want you to take a look at this in a more general form. You know what the pKs are for, and you just take a look at them individually. Okay? If you're at a pH below that value, then you're going to have the proton on that particular group, whatever it is, a side chain, a acid, or the amine group. If you're at pHs above it, then the proton's going to be off, whatever group it is. So we have our acidic acid group that is easily neutralized, low pH, our basic amine group that requires a higher pH to deprotonate, and we have side chains that are ionizable. But compared to other organic acids, how strong is that carboxyl group on an amino acid? We know if we take a look at the table that I showed you a few slides ago, the average pKa is 2.19. We look to other pKa's, knowing that a lower pKa means a stronger or weaker acid. A lower pKa, what does that mean about the strength? It's a stronger, right? Because remember the lower means higher Ka. Lower pKa means a higher Ka. and it's products over reactants for the Ka. So lower pK means a stronger acid. So acetic acid, which is it's a 2-carbon organic acid, it has a pK of 4.76. Look at that. Look at how much lower that is. Remember, this is log scale. P function is a log function. So acetic acid, which is just a 2-carbon carboxylic acid, has a pK of 4.76. This has a pK of 2.19. The only thing different between acetic acid and our amino acids is that you have the amine group on it. Really, that's the only difference. So you have acetic acid, you have 2 carbons. 1 carbon has the acid group. On an amino acid, you have carbon with the acid, the alpha carbon, and then amine group on the other side of that other carbon. So what happens is we have an electron withdrawing functionality of our amine group, which stabilizes the form that has donated the proton. And that makes this acid more readily able to more readily give up that proton. So the proton dissociates easily. So I'm not going to ask you for this definition, because you would have to have organic to fully understand it. But I do want you to know, in general, the carboxyl group, the acid on an amino acid, is a stronger organic acid than comparable organic acids. How about that amine group? How hard is it to deprotonate or neutralize compared to other nitrogen bases? So it is 9.47. So it's compared normally with 10.76 for other secondary nitrogen bases. And so here, again, excuse me, that proton is going to dissociate easier. It's not going to hold on to that proton as strong as other nitrogen groups. And then just briefly, the ionizable side chains, the basic ones, those keep the proton more than other bases. So it's the opposite. It keeps the side chain more than other bases. This is due to resonance, keeping the protonated hydrogen in. I'm not going to ask you questions about the side chains. I want you to know these things, that the acid is a stronger acid, and the base donates that proton, gives that up a little bit easier than our comparable nitrogen bases. Okay, just like any other titration, we can calculate, because this is a chemistry class, of course we've got to make it a calculation. We can calculate the relative concentration of the base to the acid. The proton off is the base to proton on. What is that ratio of the conjugate base to the acid? And we need the pKa for this. So let's just say it's 2. Let's just say it's 2. And what we're going to say is, what at a certain pH, I'm telling you that on one of the questions I'm going to ask you, what is the predominant form? Just what is present more? 50, is it 50? I'm not asking you if it's 51 to 49, all right? But we can calculate what that ratio is, and based on the pKa and the pH that we're asking. So what we can do is we can take the Ka of neutralizing this this acid. Okay, when this donates the proton, okay, it becomes the conjugate base and the acid. So here, what we're doing is we're saying, okay, let's take the Ka of this reaction and have the ratio of the base to the acid, and that is just the Ka over the hydronium ion concentration. So here, does everybody agree? This is the Ka for this reaction, right? And then what we're doing is we're just dividing both sides by the hydronium ion concentration to get this. So here we're having that ratio of base to acid. What we want to know is a little bit more information than what is just the predominant form. We want to know how much do we have of each. So what we can do is just with the Ka and the pH. So let's say we're at pH 7. And if we have a pKa for that acid of 2, what is the ratio of base to acid? What do you think? What is going to be the predominant form first? If we're at pH 7 and there's a pKa of 2, remembering from the other slide, pKa of 2, we're at pH 7, which are we going to have more of? The base, right? The proton off. And so here, we're going to give it a number. What is the ratio? So a pKa of 2 gives a Ka of 1 times 10 minus 2. Remember how to do that? Right? Go from a pKa to a Ka. You take 10 to the negative pKa, and that gives you the Ka. Just like pH and hydronium ion concentration, it's the same thing. Nothing new here. So here, pH 7 gives a hydronium ion concentration of 1 times 10 minus 7. So by doing this math, we can see that there's a ratio of 1 times 10 to the 5th to 1 of base to acid. That means we have 1 times 10 to the 5th, so 10,000 times more base than we do acid. That means that virtually, at pH 7, virtually all of that molecule, our amino acid, has the proton off and has a net charge of -1. Almost all of it. So you see why this comes into play. We need to know, okay, how much? Okay, we're above the pKa, but how much of it is really going to be negatively charged? We're going to repeat this at any calculation, any pH. You can do that.
So what numbers are you going to give us today?
I would have to give you the pKa, and I'd have to give you the pH, right? The Ka and the pH. I'm not sure I'm doing this. I just want to show you that you can do this.
You said you're going to put pKa and pH?
If I were to give you this question on the exam, then I would, I'm not saying it's a definite, but I would like you to know how to do this. I would have to give you the pKa and the pH. You can also use Henderson-Hasselbalch for this. pH equals pKa plus log base over acid. You could do it that way as well. So we're going a step further than we did in that original slide where I had the pHs of 1, 7, and 11. And I said, okay, what's the predominant form at pH 1, predominant form at pH 7, predominant form at pH 11? Here I'm saying, okay, we're at a certain pH. What is the ratio? How much do we have of the base form and the acid form? And it's really easy to do. It's not a hard calculation to do. We can do the same thing. Here for the amine, let's say that the pKa is 10. We're just making that up. So here the amine group on our amino acid. Here's the reaction when it donates the proton. And we're going to write the equilibrium constant and then divide by the hydronium ion. So here's ratio of base to acid is going to be the K over the hydronium ion concentration. It's the same as before. And so this is the same thing. The Ka we said was pKa of 10. So it's 1 times 10 to the minus 10. And if we're at pH 7, I'd have to give you that. Then the hydronium ion is 1 times 10 to the minus 7th. So here, the ratio is 1 times 10 to the minus 3rd. What does that mean to you when it's 1 times 10 to the minus 3rd? Yeah, that you have 1,000 times more acid form than you do base. Really, this is the same as 1 over 1,000. So that means we have 1,000 times more proton on than we do proton off. So basically, it's almost all in the acid form. So you can predict how it's going to behave chemically. If you say, okay, at pH 7, that proton is off my acid form, essentially all off, and it's all on my amine group. I know. Bear with me. I'm almost done. So again, it's easier to do it with the Henderson-Hasselbalch, but I like to show it from the simplicity by using the equilibrium constant. So you can look at that ratio of the base to acid, proton on and proton off. I'm not going to go through the calculations right now. I just want to finish up chapter 3. Okay. Let's move on and talk about that isoelectric point again. It's a pH in which the majority of the molecules have no net charge. So they can have charges on them, but the net charge has to be 0. So if you have a amino acid that does not have an ionizable side chain, then it's just the average of the two pK values. It's maybe midway between the pK for the acid and the amine group. So you just average the two. Not so hard. The isoelectric point is a very, very important parameter for our proteins and our amino acids. Now, I want to say something about calculating them for a protein. What people do is they take a look at your chain, your peptide chain for a protein, and they take a look at the side chains, and they do the exercise at pH, say they are at pH 8. They look at pH 8 and they say, okay, is the end that has the free acid charged or uncharged and the free amine charged or uncharged? And then they take a look at the side chains. They say, okay, at this pH, are they charged or uncharged? And based upon that, they can make predictions on the way that they're going to fold. Because if it's charged, then a positive and a negative are going to might come together. Now, when we calculate the isoelectric point, doing it that way, okay, let's say we have a bunch of side chains that can be charged. Let's look at the pH in which the whole protein is no net charge. The same number of positive, the same number of negative. But what happens is there can be a calculated one that we take a look at the side chain, the chain that's unfolded, and you'll see a certain pH. But in reality, when the protein is folded, some of those charged groups are hidden. So what we have is a calculated isoelectric point for a protein based on just looking at the side chains, and a real isoelectric point based upon observations, based upon the folded protein. Let me just tell you a little story. Large proteins don't like to be at pHs at their isoelectric point. They want to be charged. They want to have a net charge. And what happens to large proteins at their isoelectric point is that they precipitate. They fall out of solution. That's bad. I did some isoelectric focusing where you move a protein to its isoelectric point with a very large protein, tubulin, and it would just crash out of solution and cause all sorts of problems. But we had, I worked for an unnamed company, and they formulated a drug and at a certain pH and injected it into their patients in the clinical trials. And at the end of the clinical trials, it failed miserably. And one of the things that caused it to fail was having a immune response to the drug, and that you cannot have. That takes it totally out of the market. You can't put it on. And one thing that may cause an immune response is when you have precipitated protein. The immune system will go right to it. Well, some people had told me, and I never confirmed, but that there was injection site reactions, so a little redness around where the patients were injected. And they speculated is because the protein that they were injecting, the formulation was at one pH, and that the injection, your blood was at another pH, and that when it went from the formulation in the vial to the blood, it crossed the isoelectric point. And when it did it, it just precipitated at the injection site and caused that reaction. So this is why this is so important, and you need to know about it. So you think that these things that we're learning about don't have direct applicability to things that you guys will be doing in the future. It certainly does. And isoelectric point is a very important thing. It's another thing that characterizes a protein. So, molecular weight of a protein is something that characterizes it, right? Isoelectric point is something that characterizes a protein. So people will say, I have this protein because when I did this experiment to have it travel to its isoelectric point, it came out at this pH. So it's an identifier for a protein. You guys just do not seem as jazzed as I am about this, but it's pretty exciting, I have to say. Okay. Now that we've covered amino acids, probably more than you. Did you ever cover amino acids like this before in any other class? No. Okay. Well, let's start putting them together. Covalent bonds join our amino acids, and they're called peptide bonds, also known as, what are they also known as? The peptide bond is also known as one of our functions, an amide bond, that's right. It's known as an amide bond. So what happens is we condense, remove a water molecule, the amine of one amino acid, and the acid of another one. We're going to remove 2 hydrogens from the amine and then 1 oxygen from the acid and form a covalent bond called the peptide bond. And I think this works. I think there might be a commercial, though. Oh, no, there's no commercial in this one. Look at that. How cool is that? This is what I do with my free time.
Do it again.
Do it again. Come on. Go. So see the water molecule going away? The hydrogen. It depends on the charge, what's going on. So hydrogen here, the OH here, you remove a water molecule. Come on. And then you form a bond here. Pretty cool. I'm not going to ask you to draw the reaction, but I want you to see that it's a condensation reaction. I do want you to know that the peptide bond is formed between the amine of one amino acid and the acid group of the other amino acid. And that water is removed from this reaction. So here we can do it. That's why peptides and proteins are called polymers, because we're putting together a bunch of them in the same reaction. And so we get our peptide bond. So, and water is lost from it. And notice that we have the different R groups hanging off. So here we call this our backbone. You have an N terminus and a C terminus. N terminus is where you have your nitrogen, your amine group free, and the C terminus is where you have the acid free. So you have your N terminus, alpha carbon, carbonyl, nitrogen. So this is your peptide bond. Alpha carbon, carbonyl, nitrogen. That's your peptide bond. Alpha carbon, and then here's your C terminus. So here it is a nucleophilic attack. It's a condensation. Lone pairs on the nitrogen are going to attack our partially positive carbon of our carbonyl. Now, if you look at it, this nitrogen should have a lone pair on it. So it should be sp3 hybridized, which is it's from the 4 electron groups around the nitrogen. And so it should have a tetrahedral shape. However, when they do experiments to look at the geometry, this is not sp3 hybridized. It is actually sp2 hybridized, meaning that is trigonoplanar. We would expect this carbon to be trigonoplanar because it only has 3 electron groups. But this one is perplexing. Why would this be actually sp2 hybridized or trigonal planar. What's going on there? The lone pair is doing what? It's moving around. It's moving around because you have resonance structures. And let's take a look at that. So here, I'm talking about this nitrogen. This is what we're thinking. This nitrogen should have this, okay? It should have the one bond with the carbon of the carbonyl. This is our peptide bond right here. The hydrogen, the alpha carbon right here, and the lone pair. This is what it should have. So it should have the 4 groups, which makes a tetrahedral shape. But it doesn't. What happens is that these lone pairs are actually in resonance with the lone pairs, the double bond. Whenever you can have the double bond travel around, okay? The double bond can travel around through resonance structures. The reality is not that it does travel, okay? We don't have a flipping back and forth. What we have is double bond character throughout this entire thing. And when you have resonance structures, when you have the ability for those pi electrons to travel around or spread out between more than one bond, then it makes a very, very stable structure. So this peptide bond is planar, is rigid, because double bonds don't have free rotation. That's right. They don't have free rotation. So that peptide bond does not. That has huge implications on the structure of our proteins. Huge implications. There's only free rotation around our alpha carbon. There's not free. This is rigid. So the single bonds, they can rotate. Double bonds, you can't. So it's a very stable structure. So because this, okay, we're going to show the double bond character here as these red dots. So what happens is when you have your chain, your polymer of amino acids, you have the peptide bond, which is rigid. There's free rotation around the alpha carbon, so we have that tetrahedral shape. And then your R group hangs out. But what happens is the peptide backbone actually is a zigzag shape, and we'll show that next slide. But in that zigzag shape, your R groups go above and below. So let's say we take a protein and we string it out. And I pull on both ends and just make it straight. What's going to happen is that in successive amino acids, R group down, R group up, R group down, R group up. And so they go back and forth. That has huge implications when we start folding our proteins. So here, the red are nitrogen, the blue are oxygen, and the black are carbons. Here we're showing the N-terminus here and the C-terminus here of our peptide. And you can see the backbone, okay? Remember the backbone. Nitrogen, alpha carbon, carbonyl. Nitrogen, alpha carbon, carbonyl. Again, so that's what I'm talking about, the backbone. You guys need to know what I'm speaking about when I say the amino acid backbone. That means that the R groups are dangling, ready to interact. So we can see the glycine is above it. Here's a phenylalanine. Here's another glycine. Here's an alanine. Here's a leucine, a serine, a glycine, another alanine. What's that guy? A glutamine. No, glutamic acid. Sorry. And the C-terminus. So here you can see that it's up, down, up, down, up, down. Opposite sides. When we get to beta sheets, that's going to be very important. So here we're showing a small chain, which is our peptide. It's a shorter chain. If it's just 2 amino acids, we call it a dipeptide. Surprisingly, if it's 3, we call it a tripeptide. But then once we start getting more in there, we call it a polypeptide. Then we definitely change the definition to a protein. Again, here's a different definition. And I throw that in there so that you guys are familiar with it. Sometimes it's 5,000 Daltons or grams per mole for the cutoff. Again, we're going to say 50 amino acids in this class. But some of these dipeptides, tripeptides, are, when you have just a small one, are biologically active. So just like we saw, single amino acids are biologically active. Here we have some dipeptides that are biologically active. Here's beta-alanine. So here's it just has two. It doesn't have just an alpha. It's a beta amino acid. And does anybody know what carnosine does? Anybody? What time is it? Did I go through the whole class? No. I have 10 more minutes. Does anybody know what this does? No, it's an antioxidant. Here's a polypeptide. Has a dicyl bond. What is the difference between oxytocin and vasopressin? There's only one difference. There's, I think, let me see. There's two differences. In position 3, isoleucine and phenylalanine, and position 8. So there's 2 amino acids. And what does oxytocin do? Yes, that's right. And vasopressin is very different. It increases blood pressure, right, and reabsorption of molecules into the kidneys. So look, very different, right? So that's very good. All right, I'm going to give you guys your quiz. But is there any